And anybody who wanted to break into the secret message, they could just tap the phone away or something. Okay, but now we have these quantum systems that they're in this superposition. But when you measure them, you collapse them. And you don't know what they were doing before that, right? I'm going to send you a big stream of photons. If somebody comes in and like steals the photon and then passes them on to you again, like they've collapsed them, right? Do you see what's happened?
Ah, yeah.
So now, because they've measured them and collapsed them, they don't know what I sent.
Ladies and gentlemen, people of the internet, welcome to Mind Gap. You're live here with Roy and Simo, and we have a special guest with us in the studio, Dr. Ben Brown. Welcome to the show.
Hi. Thanks for having me.
Your work is it's basically, from what I've read, it's groundbreaking in a sense that this is kind of enabling quantum computation, because the problem with quantum computation before was there'd be errors depending on, I don't know.
Well, actually, could you give us a quick description of what you do? Because you're talking about quantum physics and I'm not overly following. So what exactly is your field?
I work in quantum computing.
Right.
So what we want to build, what lots of people around the world are trying to do right now, is build a quantum computer, which is a machine that processes a different kind of information, quantum information, and by making a computer of different things to the standard ones, like the ones I'm looking at around me now.
Yeah,
they can do different things and they can solve different problems.
Right.
More difficult problems that regular computers can't solve right now. But that's a really hard problem. Trying to build one of these machines, because it's based on quantum physics, and that lives in very cold places and with very small things. So you have to isolate small cold atoms or ions or all kinds of things, photons, and control them and use them and build this new information processing machine that exploits quantum mechanics to solve these hard problems. But they go wrong. So my research is all about finding ways of fixing the pieces that go wrong. And
so you've got like qubits.
Mm-hmm.
So is a qubit like a form of memory, or
it's short for a quantum bit.
Oh, okay, right.
So a classical bit is a 0 or a 1.
Yep.
So if it's not quantum, it's classical.
Okay, right.
So that's a word I say a lot. Right, and your bit can be in 0 or 1. We have lots of zeros or ones flying around. That's how we encode information.
Yes.
But quantum bits, qubits, they are quantum mechanical, and so they can be in 0 or 1. But they can also make superpositions. They can entangle with each other. They have wave-like properties
until you observe them.
Yeah, and then you measure them and they collapse, and they decide what they were doing. But you can think of, if you've heard of Schrodinger's cat, that's an example of a qubit.
No, the Schrodinger's cat. What's that about?
Schrodinger's cat. The idea is, well, as I said, quantum mechanical things we tend to think of as being very small.
Yeah.
And as I say, you can think of trapped ion. Like I talked to some people who work in a trapped ion lab, and they make an atom, they isolate it, and they knock an electron out so they can trap it in a magnetic field. It's very cold and very small, and then you can use that to make a quantum bit, a qubit. But then the question is, like, why is it only when things are small and cold? But we know that quantum bits, they can be in two places at once, or they can be doing two things at once. And then the question is, well, why is it only small things? I mean, you're not in two places at once. So when what does small mean and what does big mean? So what Schrodinger proposed is a thought experiment where you take something quantum mechanical like an atom and you put it in a box next to a bomb, and then the bomb is hooked up next to this quantum mechanical system where the bomb will blow up. Your qubit is in the state 1. It's fine if it's in the state 0, but it's doing two things at once, right? So you put all that in the box with a cat. And
I didn't know about the bomb bit. Yeah, okay.
Yeah, that's right.
Okay.
That's right. And then you can say, well, that qubit was being both 0 and 1 at the same time, and then that means that the bomb was both exploded and unexploded at the same time.
Right.
But
Right.
the cat is dead and alive at the same time, and you don't know what's happened while the lid is on the box
Until you open it.
until you open it, right?
okay,
So now the
yep.
cat is doing something quantum mechanical, and then it's something you have to think about. So why aren't cats doing two things at once? And that's a difficult problem to understand. The cats call it the measurement problem.
Wow.
This reminds me of, I'm pretty sure this is the double slit experiment. They're shooting the wall
Yep.
with, I don't know, was it electrons?
Photons,
Photons,
yeah, or
right.
it can be electrons too. You can do it
They're
with
shooting the wall
Yep.
through a slit.
Yep.
And you get this interference pattern
Yeah. Yeah.
on the
Yeah.
wall. And then when they shoot it through two slits, actually, I forgot now.
No, that's right.
Yeah.
That's right. I mean, so light behaves like, let's do it with some photons, right? So
Yeah.
light behaves like a wave, and
Yeah.
waves interfere, right?
Mhm.
When
Like waves on the beach.
waves
Yeah,
on the beach,
yeah,
that's it.
that's
Yeah,
right.
like if some waves are running this way and then they run on top of each other. They
Yeah.
add up, so you get peaks and troughs.
Yeah. Cool.
Lights
Yeah.
are the same,
Yeah.
and you shine some light at a pair of slits, right?
Yeah.
So you have one wave coming through one slit and another wave front coming through the other slit, and then you see what they're doing on the wall, right?
Right, yep.
They interfere.
Okay.
I'll tell you what, if you have a laser pen and a CD, if people have that, you can see one of those. Just
You know what?
I don't know if you have that. Because I mean, a CD is just a bunch of slits.
Yeah. Yeah.
So
Yeah.
if you have a
Ah.
laser pen and a CD, it's monochromatic light. You can shine your laser pen down on the shiny side of the CD, and you'll see it reflected on the wall. You see a little bright dot, little spots.
Yep. Yep.
That's an interference pattern. Yeah.
Well, yes, the same thing is in our field is moire. We call it moire.
Mm.
You know, when we're shooting a fly screen with
Yes.
a mobile phone.
Yeah.
And you see an interference pattern because of the grid of the camera and the grid of the fly screen. And then if you tilt the camera 30 to 45
Yeah.
degrees,
It pretty much
it goes away.
disappears.
Yeah, that's it. It's everywhere. It's everywhere.
Yeah.
Right, but the
So that's on the wall.
that's it.
Yeah.
So you got this interference pattern. And that's little pieces of light, and the explanation for that, like classically, the explanation for that is the light is a wave.
Yes.
Right, and there are two beams of light coming through those slits to interfere with one another. What we were able to do is quantum mechanical objects, like real physical things, they behave this way. So what we're able to do is reduce the light going through, and so quantum mechanics, it's quanta of stuff. So the idea is that light is particle-like as well. We're
Yes.
able to shine just like one photon, like we just reduce the number of photons going through, like a beam of light. That's lots and lots of photons. Like this, right? Gajillions coming out of there right now.
Yeah.
But then you get it down to just one, it still makes this interference pattern. Right, and that's what we see. We don't have a good explanation for it.
So you're shooting one at a time.
just one at a time,
and it still ends up, if you count them, it makes an interference.
it still makes the interference pattern. And the only way, the way that we think about this is we just imagine that the one single beam of light
Yep.
hasn't made its mind up yet. Slit it's going to go through,
Right. Yeah.
so it picks both, and then what it's doing is it's interfering with itself,
Yes. Yes.
and so we call that quantum superposition.
right.
It could be in many
So,
places.
what application would that be useful for?
This is the big question. Yeah.
Because
So
I understand what you're saying, but what application could you utilize that?
this is so now we're up to the stage where we understand that these are waves. If you try and measure it, the wave collapses.
Yeah, it decides, right? I mean,
That's when it decides, right?
yeah, that's
Okay.
it picks which one it was doing, but it had to have been doing both until you made it make that decision. And it's not just light that does this; it's also electrons and small, massive things. And in principle, cats are doing it too. But
Yeah.
I don't think we've ever superposed a cat before.
Right. Is that because we just didn't have enough time?
I don't.
We
Well,
had
no,
a Google-
I think people tend to imagine it's kind of always being observed by something or other. Like if I'm not looking at it, then something else is or some light is bouncing off of something, and so everything.
Yeah.
Like I'm looking at you, so you can't be doing anything quantum mechanical, right? You're being watched.
too many photons.
Yeah.
That's it. They're coming
that's
up and
right.
bouncing around.
That makes sense. So we're too big, and there's too many particles hitting us. All the quantum stuff just stops. Waves are all collapsed, unless you get into a Bose-Einstein thing.
Yeah, that's it. So people even make money. There's a business whose name I forget, operating in Australia. Right? You can make random numbers with it, for one thing. This is a big problem.
Like random
Random numbers.
Yeah.
Not
Right.
seeded.
Yeah,
Not
it's
seeded.
That's it. Yeah, I mean, you know,
because it wouldn't be it's completely random.
It's intrinsically random. Yeah.
Yeah.
You don't real random number generators aren't really random at all.
No.
Don't they pick something like the date?
Yeah.
Put it through or something.
Yeah, that's right. You if you're writing some code, you ask your computer what the time is, and it tells you how many seconds have passed since, like, I don't know, the 1st of January 1970. That's your random seed, and then it can make a list of random numbers that way. There's one in Canada that does it with whatever quantum system they've got in their lab.
Wow.
Yeah.
And this is important for cryptography.
Yeah, that's right. That's something else. So here's the thing. You can use this quantum randomness to send secret messages. So that
these are like a key.
Yeah, quantum key distribution. I mean, it's like this. So you have your quantum bits. Your bit could be, let's say, if the light goes through the left slit, it's in the 0 state, and if the light goes through the 1 side, it's in 1, right? Yeah. And that's conveying some information. Like anybody who wants to send a secret messages, what they need is a key, right? So I have a list of numbers and you have the same list of numbers, that's the key. So I take my message that I've encoded as a number, I add the key, like it's the add those key. Two. Yeah, that's the key, and I send you the message with the number added on. So it makes no sense. Like it doesn't make any sense to anybody who doesn't have that number, but you know what that number is. And then you take it and you subtract that number and you see the encoded message underneath. That's right. Wow. But now for me to get that key to you, that's hard. Like we have to meet up, or I have to ring you up. And anybody who wanted to break into the secret message, they could just tap the phone line or something, right?
Which technically is a good thing. If it's a secret message, you want it to be hard to crack. Right.
Yeah. Yes. Yeah, of course. Yeah, that's it. Okay, but now we have these quantum systems that they're in this superposition. But when you measure them, you collapse them. And you don't know what they were doing before that, right? They just made a decision to go 0, 1. Yeah. So this is a big problem. So if I'm going to try and share this key with you, I'm going to send my information using quantum mechanical systems instead of just, classical. I ring you up and just tell you the number on the phone. That's no good. Yeah. I'm going to send you a big stream of photons, and I'm going to encode the key that we're going to share in that. If somebody comes in and like steals the photons that I'm sending to you,
middleman attack,
middleman attack, and then passes them on to you again, like they've collapsed them, right? You see what's happened?
Yeah.
So now, because they've measured them and collapsed them, they don't know what I sent. They just know the numbers that they measured,
which will be of no use to them.
It's like security.
Yeah, it's security. That's right. So what can they do? I mean, they need to send you the message I'm trying to send to you, or the key I'm trying to send to you. Yeah. So they have to make up. They've measured some stuff, but they can't guess exactly what I sent because they've collapsed it. They don't know what I did.
Yeah.
To these quantum bits before I sent them. They just measured them, so 0, 1.
Yeah.
And they're going to send them on to you. And then, what we can do now is check, right? Like I know what I sent to you, and so we could I could send you a really long key, and we'll say like, okay, we're going to check to see if we'll take a little sample out of that key, like we'll take the first 10 digits or something, and we'll just read them off to each other. Like, okay, we're not going to use that in the key. We'll throw them out afterwards. But if your numbers don't match up to my numbers, then we know somebody has looked, and they've tried to copy the photons and send them on to you, right?
Is there a specific name for that? Like it's not like quantum security measures.
Quantum key distribution.
Oh, okay, right.
That's what we call that. QKD. Cool.
Yeah.
So you would need a point to point. You couldn't even relay it through a router. You would have to be line of sight to the other side.
You can get it. I mean, you can send your photons through all kinds of stuff, fiber optics, or you can send it, or just through in fact, there was a few years ago, they did an experiment with this through a satellite between China and Austria,
and it's going through all this hardware, and it's still not collapsing.
Yeah, that's right. The photons. I mean, photons don't interact with anything.
It's the actual photons.
Yeah, they send photons.
The photons itself go through, of course.
Yeah, they bounced them off the satellite from China to Austria, and they were able to share a secret key this way.
Oh my gosh,
that is a really awesome application for that.
Right.
In the security field. I mean, there's tons of applications.
But are these individual photons?
Yeah.
Because couldn't they just siphon a few off and read it, and you wouldn't know? Or
I mean, I don't know how many photons they sent. I imagine quite a lot. Right. Once you can make one, you can make hundreds of them, and come out of the sky, right?
Yeah. Okay.
Wow.
This is amazing.
With quantum mechanics as a general, is reducing the heat that you produce, is that a major obstacle to
Yes.
overcome?
Yeah, that's a big problem.
And what is it, like liquid nitrogen or?
It depends. It depends. There are lots of different qubits. A photon, for example. We're trying to build a quantum computer. We don't even know what to make it out of yet. It could be made out of photons. But the problem with those is, they fly off.
So you make the photons by like an ion might.
An ion, so an ion, that's something else. They have some spin degree of freedom, and you can encode a qubit on a spin up or spin down. And you start with an atom, and you knock an electron off of that atom. So now it's charged, right?
It's an ion.
It's got a positive charge, and then you can pin it in a magnetic field.
Yes.
And it's wild. There's so much physics just in how they have to do that, right? You can't squeeze it. You have this magnetic field that confines it, and but you can't. It's kind of like you can't squeeze it too tight. Like if you have a wet bar of soap and you squeeze it, and out the top, right? That's what happens.
That's
so they
right.
actually have. So they need to move this magnetic field around and around and around.
Yeah.
So it's like. So it's always going to fall out.
It's
but
like
it's
a
always
bowl.
falling out in a direction, Right. Yeah. So you have to spin the bowl around. It's like Pringle shaped.
Yeah.
Right? You have a Pringle, so you let it roll off on one side, and when it starts to roll, you spin it around again.
Yeah. Right.
So you have this. So it's got this
gosh.
spinning potential, and and they have to and you can't observe it, and nothing can, not just me or you, like nothing can observe it. So they have to, like, for example, a piece of air, like some air molecule hits it, that's going to screw it up. That's a measurement that's going to go somewhere else, and you've lost some information. So you have to suck all the air out. So in these labs, if you go into one of these labs, they're very dark, and they're always in the basement because they don't want lasers shining out the windows and in someone's eyes. And they have this big, I think it looks like a diving bell. So they can suck it's this big metal thing with some windows in the side, so you can shine your lasers in. And you use these lasers to control it and to move it around. And they suck all the air out of this diving bell. They make a complete vacuum. Or the best vacuum they can.
Very close to the air.
Yeah, that's right. And they pin a bunch of electrons, ions, all in these traps.
Wow.
They're little. They have more sophisticated ones, but the ones I learned about were like a quadrupole trap. So you have 4 little
magnetic fields.
rods, they conduct electricity and then spin this magnetic field around.
They don't use what do they use for fusion? Tokamak. They don't use a tokamak.
Oh, I don't know about that. They have these big Helmholtz coils though.
Right. What happened to the electron? The photon that comes off. You just is that the one that you're using to?
I mean, that's a different kind of qubit. I mean, you can talk. I mean, this is going to be another problem, right? A quantum computer. Do
you know what color the photon is when it flies off?
Those ones are optic. I mean, they're visible light. They produce visible light. Yeah, no. And then we're talking about a lot of things I don't think about too much every day, but it's crazy. It's great. No, it's all right. It's okay. I'm just hearing all the voices of these people who are going to tell me. I'm saying
No. All good.
And that's right. They the light will couple with the ion, so you can shine light into these ions. They have this spin degree of freedom and this vibrational mode, and the light recoils, and the ion feels some pressure from the photons, and this is how we control it. So we have these lasers shining inside this diving bell, this big vacuum chamber, and you also sometimes need to make them communicate. So you can make an ion throw a photon out, and it will talk to another one. So this is going to be a big problem that we have to deal with, and it's getting a little close to kinds of things I really think about, which is how are we going to make a quantum computer bigger? Like we're pretty good now. Like the people in the lab, they're very good at controlling 5 or 10 or 20 qubits, a handful, a bunch. You can go online and IBM, they let you use their little qubits, like 5 of them, which, I mean, they don't, I mean, it's like a little quantum abacus. It's not a quantum computer yet. Those are superconducting ones. So those are little electronic circuits in this dilution refrigerator. They make funny noises like Darth Vader sounds like.
Oh, really?
Yeah,
cool.
It's funny noises. And it's going to get harder and harder to scale them up. So like if you have 10 or 20 ions, that's not going to make a quantum computer. But now I've talked to some people in Oxford sometimes, and what they think about is how do you make 2 ion traps, the ions in this trap and the ions in this trap, how do they talk to each other? And they're doing lots of experiments right now, trying to figure out how to get one photon out of here over to here, so that the 2 different ions and 2 different traps can talk to each other. And this is how you're going to get, I mean, when you talk about when you talk about a computer, you don't talk about bits or bytes, you talk about gigabytes. Millions and millions and millions of them, and it's a really big problem trying to work out how to control all of these quantum systems. To build a big quantum computer that we need, the kinds of numbers of qubits we need to do interesting things.